Okay, so on Wednesday we have some presentations. So just make sure to those of you presenting bring your slides on a PDF version of slides on a USB stick, or send them to me a little bit in advance so that I can load them on the laptop. So the agenda for today, I'm going to wrap up the scheduling, and we're going to start on time synchronization, clocks and time. That's kind of the next topic. The other thing is, one thing I kind of realized was that when I handed out the dates for the remaining presentations, I missed December 8th, which is actually the last day of classes. So I will actually be shifting the presentation dates a little bit, because some of them will also be on December 8th. So I'll be announcing them fairly shortly. Okay, so last time around, we were looking at scheduling using earliest deadline first. And I had gone over kind of the main results out there, but main thing, nice thing about, just give me a sec. A nice thing about EDF is that it can, under certain conditions, it can schedule anything which has a processor utilization, any task set which has a processor utilization of 1. And that is the case when I have deadline equal to period. But if deadline is less than period, then kind of a more elaborate way of testing it kind of boiled down to, and it's in effect again testing whether the amount of work that needs to be done is less than the amount of time that was available in any arbitrary time interval. And that had basically boiled down to looking at that whether for all possible durations L, whether a certain condition, which is kind of the work that needs to be done, or amount of computation time needed is less than the amount of time available. And kind of the main thing was that we only need to test it for select values of L, which correspond to the deadlines that would occur there. So kind of the typical approach was we start out with saying we don't need to check beyond the hyper period. Then there was also this additional L star, which was kind of another limit we had derived, that we only need to check up to that. And then the idea is from 0 through L star, you check 0 through minimum of L star and the hyper period, you check at all possible deadlines. And if at any place there is a violation that happens, you have a problem. In this particular example that I had shown, it turned out a couple of places here and here, we were just meeting the amount of work done and amount of time available was exactly the same. So this task set was schedulable, but it is barely schedulable, so I cannot slow the processor down. So what kind of that wraps up kind of the two main sort of results that exist when it comes to scheduling in real time on a single processor or single resource, which is rate monotonic inspired stuff and EDF inspired stuff. One is static priority, the other is dynamic priority. Major advantage of fixed priority, which is rate monotonic and other fixed priority assignments, is that it's a lot simpler to implement, because you don't have to mess with the priority at runtime on a continual basis, and therefore both in terms of hardware and as well as software realization, it's a lot easier to do this thing. But at the same time, what's also true is that the overhead of maintaining that priority list matters really for systems where there are lots of tasks. So for example, on a network switch where there may be many different flows of packets, then this is an issue. But on a typical embedded system, you may have a very small number of tasks, and this particular issue, that rate monotonic, that fixed priority is easier to implement for the OS, is probably not that important. Having said that, there are very few implementations of EDF which are around. You'll find fixed priority very easily in embedded OSs, but not EDF. EDF also has problems analogous to priority inversion. So in priority inversion, the problem was that some resource gets locked by a low priority task and sort of other tasks kind of take a hit. It's the same thing out here also. This concept certainly possible that a resource has been locked and then one has to kind of deal with this thing. There are similar mechanisms that have emerged for EDF also to cope with this. The main thing otherwise is that sort of having that EDF offers advantages. The biggest one is that it can schedule more task sets, or equivalently, you can get away with a slower processor because the utilization bound is 1. So that works great. And most of our systems actually do tend to have deadline equal to period. I mean, that's typical sensor type processing and all. You get one sample, all you care about is finishing it off before the next sample. So EDF works really sort of great. The EDF schedulability test, if you can get away with u less than equal to 1, is trivially simple. But even the other test is pretty much the same as what rate monotonic does. That is, we basically are testing out what is happening over a period of time after the critical instant. Another interesting thing about EDF is that if there is overload on the processor, let's say there is a thermal event and the processor frequency has to be slowed down, then in case of EDF, everything slows down gracefully. Whereas in case of fixed priority, some tasks will start missing their deadlines and they will be the one penalized. So basically, it's an unfair allocation of slowdown in case of fixed priority. That is, low priority tasks will basically be starved out, whereas here there is everyone basically kind of gracefully slows down. So you could imagine in case of EDF, if a slowdown happens, then a signal can go out to all the tasks saying, look, there's a slowdown happening, and they can all gracefully kind of go down. Whereas with fixed priority, the low priority tasks will basically be locked out for a while. So this thing is basically, this graceful slowdown is called a period rescaling property of EDF. Okay, so that was EDF. I'm going to sort of also give you a glimpse of some additional issues that come up in when we deal with scheduling. So one very common one is that our tasks are not really independent. Oftentimes we do things where one thread may need the data that is produced by another thread. Okay, so for example, one thread may read the sensor data, supply it to something which is doing the processing, then which hands it over to something which is doing a communication. So what you really have in systems often is a group of related tasks or threads, and they collectively run at an identical rate. Okay, so it could be that every so often T1 is started, and then T1 produces some data which T2 and T3 need, and these arrows are kind of showing those dependencies, and so on and so forth. So my system usually would consist of a bunch of sets of mutually dependent tasks, and the dependence in this case is that they have a producer-consumer kind of relationship. So this whole cluster will have a single rate attached to it. So in this particular case, we at a high level, you can say, okay, each one of my cluster is kind of like a task, and I can deal it with a in some sort of framework, but EDF for static priority. But then I also have to worry about scheduling within each one of these clusters according to the dependencies which are out there. So there are heuristic algorithms that kind of exist for this kind of stuff. So in this case, what we are seeing is that I have a bunch of tasks. I'm given execution times for them, and I'm given the deadlines for these things. So I may have so T1 at some point in time, this whole cluster arrives. T1 is released, and then T1 does its job, produces some outputs which T2 and T3 will make use of, and so on and so forth. And what we have are deadline constraints on each one of those tasks as well. So like task number 3 has to finish by time 20, and it needs 2 units of time, and so on and so forth. This is a kind of scheduling problem which is often faced, and the solutions for these things are basically heuristic in nature. That you can either start out greedily from one direction or the other. So, for example, in a uniprocessor case, what we could do is we can sort all the tasks according to their deadlines, and then what we do is we start with the task whose deadline is the farthest out. We schedule those. Once we have scheduled that task, then we can see which tasks were producing results for it, So and schedule them. So let me take as an example. So in this particular case example, we could start out by saying, look, T6 had to finish by time 28. So we put schedule T6 at 28. When T6 is pinned down, then if I go back to my diagram, we can also look at T5. So T5 deadline is 27. And I could also now look at T4, and T4's deadline is 21. So in this particular case, what we'll say is let's pick T5. So we put T5 out there. Once I have run T5, then T4 is still in my queue, and T3 was feeding to T5. Going back out here, T3 was feeding to T5, so I have to put down, I could put down T4 and T3. Now, and we are still meeting the deadline. T2 presents a problem because T2 has an earlier deadline. Going back out here, T2 has a deadline of 7. So when I'm pinning down T2, I have to leave this little space out here because I cannot push T2 past 7, and then T1. So first tab, working backwards, I would have kind of an assignment like this. And then the second phase, what you do is you kind of move everything as early as possible. So T1, T2 move out here, all of these things can move earlier, all the dependencies are met. Yeah. So this is entirely a heuristic. This heuristic can fail, can give you suboptimal results, and so on and so forth. But this is an NP complete problem, so heuristic is pretty much the only way you could do it. So this basically kind of begins to go into kind of dependencies that you're seeing within groups of tasks or across groups of tasks. Another concept which often gets used is that what. Go ahead.
But I think the problem can be less if we change the deadline of the dependency. For example, if someone depends on someone, you change the deadline to the earlier one and solve the problem as it is old problem.
Say it again. Say it again.
For example, some task depend on another task.
Mm-hmm.
For example, T4 depend on T6, and
T4 feeds into T6, right?
Yes. So T6.
T6 depends on T4, right? So yes. T4's output is needed by T6.
So you change the deadline to be the earliest deadline. Then you solve the problem without looking into the dependency.
Oh, you're saying that I can change the deadline. See, so you have to look at the dependencies because when you're scheduling this thing, you have to make sure that T4 is finished before you run T6.
Yes, but if you make the deadline before, your algorithm will finish it before you.
No, so whose deadline? You make that. Oh, you make the deadline of T4 to be So okay, so let's so what's happening in our schedule is the following, right? So we're basically saying T6 has the latest deadline. It needs to run 28, finish by 28. So therefore T6 is going to run from 22 through 28. Okay. Now, and right at step 1, I also okay. So at this stage, then candidates for me are T5 and T4. T4 clearly. T4 has to finish by 21, but this thing started at 22, right? So, so I cannot do T4 yet, but I can do T5 because T5's deadline was 27, right? So in your case, whose deadline would you want to move earlier?
I want to change the dependency by playing on the deadline.
You cannot get rid of dependencies by deadlines alone. Because deadline means that's the latest I can do, right? I mean, for example, by looking at these deadlines alone, if I were to just look at these tasks 4 and 6, and I do not look at the dependencies, one could say, hey, I run T6 first and then T4. Yeah. But that will not be valid because of the dependency, right? So the deadlines do not tell the story about precedence.
Okay, so we can, I think there's some algorithm doing that. Maybe they play on the release time.
You can have to play on the release time. And exactly. But in this case, our model is that the release is only for T1, right? Because this is it doesn't make sense to talk about release time of T2 because release time of T2 is basically a task which is saying, wait for output from T1, okay, and whenever the output of T1 comes, then T2 starts running. So the release time in this case is not explicit. Release time is that T2 is released whenever T1 is finished. Okay, but you're right that you could play with release time if that was explicitly given and kind of work with that. So another concept which sort of has been explored quite a bit also is what happens if I'm going to be going to miss a deadline. So one option is we missed a deadline and live with the consequences. Another option is what if once I realize it, I do an inferior version of the task. Okay, so I don't know, did any of you attend the talk last Monday by Dr. Raghunathan? Some of you did, Approximate Computing. Okay, so kind of this notion is in many cases an acceptable, there are possibly bunch of results which are equally acceptable or maybe acceptable with some loss of utility. Okay, so for example, maybe I asked whatever, there's a search query I'm running on Google, and instead of returning to me 1,000,000 results, it returned to me 500,000 results. For all practical purposes, is fine. Or maybe if it is, I don't know, processing an image, and then instead of processing it at the highest quality, maybe it did it with some loss of quality, and once in a while that's acceptable also. So kind of the idea out here is that what if I had multiple versions of a task, and normally I would like to do the desired version, but if I have a choice of not doing anything, missing the deadline, versus kind of doing an inferior version, then perhaps that's not so bad. So kind of notion being that worst case execution time and kind of always budgeting for it can be rather problematic. So what if instead of budgeting for the worst case execution time, we budget it for something less? So let's say I have a task whose worst case execution time is very large, 100, but whose mean execution time is, let's say, 20. So if I budget for 100, and I'm assuming that it's always going to be 100, then I'm going to need a very costly processor. But what if I budgeted for something less? Let's say I budgeted for the mean, and then if I realize that I'm going to exceed, that this particular task is going to exceed, then I go for a approximate version of the task. Okay, so let's say now I have an approximate version of the task, which instead of taking time 100 in the worst case, takes only time 10 in the worst case. Okay, but gives an inferior quality result. So what would happen in this case is, let's say I start running the task, and I'm hoping I start running the high quality version of the task, and I'm hoping that it would hit its average mark. But then 10 seconds and passed, and the task is still running, and now I have a go no go decision. I have 10 seconds remaining. I could either hope for the best and still continue running with the high quality version of the task, but then there's a chance I may miss the deadline. Or we may say, this is a point of no return. Let me switch to the inferior version of the task so that by the deadline, I still kind of finish the thing. So that's sort of the concept out here. So I have a primary version of the task, high quality. I have an alternative version of the task, which is low quality, lower quality, gives me an approximate result. Worst case execution time, 20 out here, 5 out here. Average runtime 7 and 4. Periods are the same. These tasks basically are two versions of the same task. And kind of the idea in this particular case is that at some stage I start running, and deadline is the same as the period. So my deadline is 15. At t equal to 10 is going to be the point of no return, because at that point in time, if I continue running with my high quality version of the task, there is a chance that I may miss the deadline because its worst case execution time is more than my deadline. So at this stage, I kind of switch to the alternative version. And you can imagine variants of this idea. I may have multiple versions. I may make that decision upfront. If the processor is slowed down, thermal event, slow down of frequency, I can switch to kind of a more approximate version of the task. Now, luckily, in embedded systems, these kind of tasks abound. That's point number one, because a lot of processing is signal processing, inference making, these kind of things, and they are naturally kind of tunable. I can if I'm doing let's say filtering a signal, I can just use a simpler filter. It will inject more noise, but it will still give me something acceptable. I can change with the number of bits. I can do fewer iterations of an algorithm. So there are many different sort of things can be done. Go ahead.
So basically, in this way, you're missing all the high quality tasks, which takes between 10 to 15, right?
Right.
What if you like run both of them in parallel, like the alternate and primary, and then you wait until 15?
If you had the hardware resources to do it. Okay, so the question then becomes, if let's say I did have 2 cores, could I play this game? Yes, what you're suggesting you can, but in a uniprocessor case I cannot. I cannot run both in parallel. Okay. The other thing which kind of helps in this thing is that the ratio of worst case to average runtime tends to be quite large in most sort of a lot of the tasks that you see. There was a study out of Princeton where they've kind of shown commonly used embedded sort of algorithms and all, and these ratios are often like 10:1, 50:1. Like for example, you look at things like image compression, FFT, these kind of things. They're very data dependent because certain data values result in cutting through the computation very rapidly. Other data values kind of result in a very high degree of things. So these algorithms are have a high worst case to average case problem, and the other thing is they are intrinsically tunable. The way I have presented out here, this primary and alternative, I've kind of implied these are 2 separate algorithms. They could be the same algorithm but with different setting. Like for example, it could be JPEG at high quality and JPEG at low quality. So it's not like you necessarily have to do two things. In a more elaborate version, you could even imagine that I may have an algorithm which is incremental. That is, the more work I do with it, more time I give to it, the higher quality result it produces. And that kind of leads to this next concept, imprecise or approximate computation, which was the topic of that talk on Monday. And kind of the idea is that what if I could design my tasks so that they're stoppable at any point in time, and I get more quality from them if I gave them more time. So instead of this primary and alternate with a kind of a very hard notion of I have to switch to it, what if I were to write my algorithms in this particular way? Now, of course, nothing is finely divisible, so it's not like I can just stop at an arbitrary point, but idea is that you give more time and you get a higher quality result, and then the system at runtime can decide what quality setting is going to be adequate. So I can tweak with whatever notion of quality that one may have in mind. In this particular example, let's say maybe some place I'm doing some division, and then at some I can kind of, instead of computing all the bits after the decimal point, maybe I compute only some of them. So I have an approximate result out there, and many algorithms kind of lend themselves to this kind of a model. So this kind of scheduling, this kind of approach is called where these kind of tasks are called IRIS tasks, increased reward for increased service. Service in this case is time, but it could be any other thing. It could be energy, it could be memory, it could be network bandwidth, kind of essentially more resource, better quality. And then, but if we think in terms of time in a real-time setting, then the idea is that you can think of every task to perhaps have a mandatory portion, that is, this is the bare minimum quality that you absolutely must have for it to work, and then there's an optional component, and then this optional component basically the more time, so these correspond to time, the mandatory time and kind of the optional time, and then at some stage in a typical setting, it's not as if forever you give it more optional time and there is more quality. At some stage things saturate. So usually these curves look like, I mean, there's a mandatory portion and then they kind of monotonically rise, and then at some point you stop getting any additional benefit. So a very good model is that I can think of my task as providing a reward or a utility. And if I give the task time less than m, then I get absolutely no service out of that task. So it's basically a failed. If I am in some zone n through O plus m, then I am going to get some utility, and this utility function r of x or reward function is going to be some sort of a monotonically increasing function. And then finally, if I give it too much too much time, too much resource, so more than O plus M, then I kind of saturate. So at this stage, I kind of saturate. So it's a very common model, very commonly used in networking and stuff like that. Also, besides kind of processor time, there's one operating system which kind of follows this, and which is pretty commonly well known as something called Linux RK, Linux Resource Kernel. This is a version of Linux out of CMU, and it uses this concept there, resource reservation and associated utility function, for every resource in the system. So bandwidth, memory, CPU time, kind of everything is treated in this particular way. And in this case, the goal of the system becomes that I have a bunch of tasks which need some resource, let's say CPU time or memory or whatnot, and my goal is to assign them resources X such that hopefully each one of them is getting its minimum, the mandatory portion, and the overall utility is maximized. That is the sum of the reward. So usually the reward functions are 0 through 1, so they're normalized to that, and then you basically would say, okay, I want to maximize the overall utility that my system is getting out of that. What problem do you see in this kind of framework in practical settings? Thoughts?
Maybe I guess it was some time by repeating some computations. In the mandatory part, there are some computations that have already occurred. Maybe it will be repeated again in the optional part.
Not sure I fully understand what you're saying. Anthony?
Maybe if you try to maximize the total number of reward functions, you may do that, but it's possible you'll miss one of the tasks that is actually truly critical.
Right, but kind of the idea is the system would first prioritize making sure everyone gets this N. Right, I mean, so that should. The problem is more mundane out here, which is it's very hard to know what these reward functions are. I mean, like, most of the time that becomes a showstopper. If I were to ask you, you're writing a program, could you give this kind of a reward function? I mean, it's incredibly hard. So the way these things are done usually is for certain kind of things, like for example, let's say it's a JPEG thing, okay, and it has different quality settings, okay. So now, how does quality relate to reward? It's very unclear. Quality is something that the standard prescribed, and you can certainly take an implementation of JPEG and make a plot between quality as specified by the standard and the time it takes, let's say, on the worst case image. But that doesn't really mean that it indicates anything about how well my system is doing. So what people often in some cases do is they conduct human subject tests. So they will show them versions of the algorithm with different amount of resources given and the resulting output, and then kind of say, vote on it. Okay, this is done very commonly in speech and images and these kind of things, but hard to generalize. So while mathematically this kind of thing is nice, and a lot of people in sort of use this kind of utility-based framework are very popular, because once you have this function, and if you make this function to be nicely behaved, then you can do a lot of nice math around it. But in practice, specifying this function is pretty tricky. These kind of concepts are also used in economics, kind of overall societal gain that you are maximizing, and also sort of comes from there. Yeah.
This reward function, is the reward like defined by the program, or is it defined by the OS?
Defined by the programmer, right? I mean, defined by the app. So the app is basically saying, you give me this resource X, and for any given, so it's telling the OS the mapping between the amount of resource and the value the app sees for it. Okay, so it's defined by the app, or perhaps app with some user input. Okay, but in either case, I mean, it's pretty hard to define. So that's where kind of things kind of break down. So this is kind of just an example of how in some setting things might work. There are a couple of tasks, and what this thing is basically showing is that so I can give task 1 some amount of resource and task 2 some amount of resource. I have a total of 10 units of resource. So 3 possible combinations shown out here: 5, 5, 7, 3, 4, 6. Each one of them result in some utility. So in this case, unfortunate thing is we also talk about processor utility or processor utilization. That has nothing to do with this view. This is basically saying how much satisfaction, how much reward the application is getting. So how much reward application 1 is getting if it got 5 units of resource. How much reward it is getting if it got 7 units of resource, and so on and so forth. And likewise, this is for application 2, and you add them up, and this is a total satisfaction that the system overall has. There are other problems also, like, I mean, if you see out here, you just add up individual rewards, and the thing is, can you really add up rewards? Can I take JPEG, let's say I decide that I'll normalize a JPEG quality factor as my reward function, and I do the same thing with, let's say, some acoustic thing. Can I just add them up? Are they of the same value? I mean, none of those things are kind of obvious. So, so mathematically kind of nice, but in practice, it's very hard for app developer or whatever, application developers or users to kind of deal with this issue.
Wait, what was R and what was U?
R is the resource given, U is the utility or the satisfaction that the two applications are deriving from it, and U is the total system utility. But this is what Linux Arcade that I mentioned uses. So late 90s work, but it's an operating system which is still used. And the nice thing though is that by adopting this kind of framework, it actually begins to say it's not just a real-time operating system. It can handle all sort of resources in the same framework, network bandwidth, memory, all type of things. So this model, this thing of specifying these kind of functions is often referred in literature more generally as quality of service. So I'm basically kind of saying what is the relationship between the service and the quality. Okay, more service you give, namely more resources and all, there's more sort of quality you get out of it, and in many ways this reward or utility or whatever we call it is an indication of the quality that one is getting out of it. Okay, another generalization scheduling comes in settings when we have a distributed system. So now no longer do we have a single processor, but I have a bunch of processors, and my overall task set may be divided among them. And so it could be that I have a sensor on node 1, it collects the data, there's a task collecting the data, perhaps does some front-end processing, sends it over a bus or a network. Then I have another processor where I do some machine learning and then show the results of that. So in this case, my deadline is really end-to-end deadline. Let's say collecting the data to showing the result, but it is scattered over 2 processors. Each processor will have its operating system. And what I'm really interested in knowing is that how should I partition my tasks across these 2 processors? I have a network in the middle with some uncertain delays. So you can imagine the network also has a real-time scheduler of some form, and now I'm trying to reason about the deadline. So several issues sort of come up out here, come up in a setting like this. The first part really is, which complicates things quite significantly, is that all the results that we have were really about scheduling on a single processor. So we cannot simply say, okay, if I have a set of tasks, I'm going to run them on 2 processors. If I assign them priorities according to rate monotonic and kind of dump them onto 2 processors, any of those results hold true. They don't. We don't. I mean, now we are in the world of heuristics again. So that's problem number 1. Problem 2 is that communication fabrics are usually don't give a whole lot of promise about deadlines. If you look at the delays in our typical buses or Ethernets and things like that, there's a huge spread which exists. There are certain networks now, and both wireless and wired, which do try to give you deterministic delays. They are basically, you can say, just like we have real-time computing, they are real-time networks. They give you promises about the deadlines, but they are not commonly deployed. So if you are working over your typical LAN or internet or things like that, there are no delay guarantees. You would hope for something, you'll typically see some reasonable values. There's going to be a spread, but that's pretty much where you end up with. And the other issue that one ends up often also is that I may be given an end-to-end deadline, and task of finding out how to divide it among the different things that we face. So again, my example, sensor feeds data into processor 1, I go through the network, and then I have a processor 2, and then I have the output. And I give you a deadline, let's say D, which is from the point the sensor sample arrived to the point the output has to be generated. I have 3 systems in play, processor 1, network, processor 2. And how should I divide my overall deadline among these 3? It's pretty tricky as well. Again, it's a NP hard problem. There are no good algorithms to do it. So just the task of dividing things up, and this is something we face all the time in system design. So let's take our let's say you're designing a telephony type app, okay, where you're capturing some data at one node, you're going to send it over other node and then back. Now from an application perspective, human perception perspective, there are well-known deadlines on it. Like for example, for bidirectional audio, once the delays hit around 800 millisecond or so, then conversation becomes perceptually very hard, okay, because sort of we begin to talk past each other and all. So let's say we take as our case that from the microphone to the speaker, the delay has to be 800 millisecond. But I have the network and the two nodes and perhaps other entities in this pathway. How should I divide this 800 millisecond into these three things: the sender, the network, and the receiver? Because once I have the delay budget for each one of them, then I can do real-time scheduling for each one of them. But that initial division is very hard. You can play with these numbers, you can heuristically try to allocate them, but no optimal results kind of known out there. A common strategy in these kind of things then is that you actually look at how much spread in delays that exist and you do buffering. So this is something that you would notice in things like, I don't know, Netflix, YouTube, Skype and all, which is that they buffer stuff up. And the idea is that on the receive side, there is a buffer. And you design this thing so that if things come too early, they sit there when you play it out. So you kind of essentially choose an end-to-end delay and then design your system to be much more conservative so that things may arrive earlier, but in the worst case, they may arrive late, and in which case this buffer helps smooth things out. So problems that we face out here, dividing end-to-end deadline, and also where should the work be done? That partitioning of the tasks. So if I have, let's say I'm running a collection of real-time tasks and I have multiple processor cores in my CPU, how should I partition it? Should I put all of them into one? Should I divide them half-half? How should I go around doing it? So there are many heuristics kind of have emerged for that problem also. So for example, one very common stuff is that maybe we'll divide the tasks, map the tasks to processors based upon some criterion that I may have. Like for example, maybe I'll say intuitively, let's keep all the processors equally balanced. So we'll propose a solution and then you check the feasibility. You see whether that particular allocation will meet my goals or not. So a very common algorithm, therefore, is this kind of a utility balancing algorithm. The idea is that I have a bunch of tasks, I have a bunch of processors, I have to partition them up. On each processor, I'll be running my real-time operating system. And what I do is I kind of take a look at one task and then put it into the processor, in one of the processors, and do it according to some criterion. In this particular case, the criterion may basically be to keep processor utilization balance. Every processor's utilizations, sigma u, would be roughly the same. So there are algorithms based around that. Now, for EDF, if let's say you were trying to implement something like this for EDF, okay, so I have a bunch of tasks and I have a bunch of processors. So let's say I have n processors. I have tasks. For each task, you are given the period and the computation time, and let's assume deadline is equal to period, and let's assume that you can only map a task to a processor and then not move it around. So EDF problem basically is sort of a bin packing problem. In each processor, I can have as many tasks as the utilization would be less than equal to 1. So now, done incorrectly, what may happen is I may take tasks and allocate them to processors in a way that I may preclude additional tasks to be done, even though there may be spare capacity. So this is what we call as a bin packing algorithm, and you kind of, there are heuristics and all floating around for these things. Rate monotonic is trickier because in rate monotonic we do not have a simple criterion like total utilization less than equal to 1. I need to make sure that my tasks, their deadline, their utilizations are related in a way so that they are schedulable according to the criterion we discussed. So there are more complicated ways that you will have to assign tasks to processors so that you can ensure schedulability out there. Now, in some cases, you may have a choice of there not being a limit on number of processors, but even there, optimizing it would be useful, because if you have more processors, then you're going to be spending more money or more power. So there are a bunch of examples. I'm not going to go into it other than point out that for EDF, this is a bin packing kind of an algorithm where essentially you're assigning the tasks, and your goal is to make sure that in each processor, tasks do not add up to utilization more than equal to 1. And one particular heuristic is this first fit decreasing algorithm, where kind of the idea is that you look at whichever task fits first in a particular bin, you assign it and move on. So there are many heuristics. I'm not going to go over it. There's sort of the gazillions of them out there. Next issue which comes up in this case of distributed is that what if you had distributed and data precedence? And this is where things get really sort of more interesting and complicated. So let's imagine I had a system where I had two groups of tasks with these kind of dependencies. So I have one cluster P1, P3, P5. So it could be P1 is reading some sensor, and P3 and P5 process that and generate the output. P2 is some other sensor, and its output is processed by P4. And what I may have is a system where I have three processors: PE, processing element 1, processing element 2, processing element 3, and kind of task that we are looking at is that how should we partition these things. So the point I wanted to make was that in these previous heuristics, there was no dependence. So all we were doing were our job was partition them, and then once we partition them, I can apply my traditional test to see whether each processor was individually schedulable or not, and if it was, then we are done. In this particular case, it turns out that even the problem of knowing whether this particular partitioning will meet its deadline is NP. Is the hard problem. So I cannot even rely on a strategy where I can say select a partition and then test it and then try to improve it, because even the testing problem is a hard one. So let's look at why this problem is a hard one. So let's look at something like this. So let's say I had a system like this where I had two task clusters. One task cluster has three processes in it: P1, Px, P2. So P1's output goes to Px, Px output goes to P2, and then I have another task called P3. And what I have is I have two processors given to you. So you can map these tasks, these four tasks, to the two processors, whichever way you want. The processes that we are given, P1, P2, P3, Px, they have a period. So all of these things are going to have the same period because they're part of the same cluster. So you see P1, P2, and Px, their period is 100. P3 has a period of 150. And computation times are 10. P2 is 10, P3 is 30. And Px, let's say, could be in the range 25 to 35. And let's say we decided that we would put P1, P2, and P3 on processing element number 1, and we will put Px on processing element number 2. And let's say my overall system is such that P3 has a deadline, and P3 must finish by 45. Now, imagine that we were lucky and Px came at time and took only time 25. And let's say another version of this case scenario where we were unlucky and Px came at time 35. Okay, so let's imagine that so the part which makes us this problem of multiple processors with precedence and deadline constraint tricky is the following: that for a given allocation, it could be the case that with 35 I meet the deadline, but with 25 I do not. Okay, so basically what's happening is that if I'm lucky in terms of Px and it takes shorter time, or maybe even that processor was able to run more rapidly, or I replace PE2 with a faster processor, then what was originally a schedulable system can become non-schedulable. So there is no monotonicity in this setting, and that's what makes this problem hard. So let's see why it happens in this case. So we have that particular partition, and let's look at first the case where Px was unlucky and it took time 35. So what's happening is that, and we are doing fixed priority type scheduling. So period 100 processes have the higher priority and P3 has a lower priority. So what happens out here is P1 runs, P1 finishes at time 10, produces its data, which goes to processor 2, PX starts running. Meanwhile, on processor 1, P3 is ready to run. So P3 runs. P3 will run until time 40 and then finish because it uses time 30. It needs 30 units of time. So it has comfortably met its deadline. Its deadline was 45. And meanwhile, Px will finish after 35 time units, so that means it will finish at time 45, at which point P2 will start on processor 1 and finish and be done. So in this case, P3 met its deadline. Let's consider a second case where we were lucky and Px actually took shorter time. So Px in this case would finish at time 35, and the moment it finishes, a message goes out to processor 1, and here now P2 will preempt P3 because P2 has higher priority. P2 begins to run, takes time to 45, and then P3 runs and finishes at time 50. So now what has happened is P3 missed its deadline. So this is very non-intuitive, and that's why this version of the problem is harder. So we started out with one processor independent tasks. We have great theory for that. So one processor independent task, great theory. One processor tasks with dependence, we have heuristics. They work well reasonably. And what we can certainly do is, based upon heuristics, I can then decide whether, so given a particular schedule, I can test whether the deadlines are being met or not. Then we went to multiple independent tasks, multiple processors. Again, heuristics, we map processors to tasks or tasks to processors, and we can check whether deadlines are being met. Great. But finally, in this case, where I have multiple processors, multiple tasks, there are dependents. In this case, even the problem of testing that if I map something to the processors and will it meet the deadline is a hard one. So I cannot even have an iterative loop like do an assignment, test for it easily, because changes such as making a processor faster will actually make a system non-schedulable even though it started out being schedulable. So this situation is pretty tricky. These are referred to as scheduling anomalies. There is kind of a theorem which says if a task set is optimally scheduled on a multiprocessor with some priority assignment, a fixed number of processors, a fixed execution time, and some given precedence constraints, then increasing the number of processors, reducing the execution time, or removing some precedent constraint can all increase the schedule length, okay, which is counterintuitive. That is, we are doing things which supposedly should make things faster, but they actually can work the other way. So, so that's kind of this version of the problem is just insanely hard, therefore. So this is another example, like I had a bunch of tasks. Again, arrows indicate precedence constraint. You have the execution times out here. And what it is showing is that I have an optimal schedule for the 3 processors. It kind of look like this. So I map the tasks into 3 processors. And then we play games with this thing. So what we do is, in this case, we add a processor. Okay, and again, we are going with the policy that if a processor is available, a task is ready to run, I'm going to run it. Okay, I'm not going to leave the processor idle unnecessarily. So it's a work conserving system. And you see in this case, what happens is that actually I finish later, even though I added a processor to it. Because the OSs are blindly following the policy that if there is something ready to run and there is a free processor, let's run it. This particular case, what we do is we reduce the execution time of each task by 1 time unit. So like J5, instead of taking time 4, takes time 3. J6, instead of time 4, takes time 3. We do all of that. You would again expect that I would finish earlier than 12, which is what this guy was doing. But in this case, it takes up to time 14. And the problem in each case is the weird interactions that are happening because of the precedence constraints that exist. Another one, I remove some of the edges. Okay, so there are fewer dependencies. One would think that would give a better result. It doesn't. It gives the task set finishes later. So these situations basically say that this was another problem. You're trying to doing real time over multiple resources with precedence constraint is a hard problem. So this is kind of another example showing the same thing, because what's happening in this case is I had some tasks scheduled on the system, but then we did something so that J1 computation time is reduced, and we reduced J1's computation time, but actually my overall schedule length increased tremendously in this case. So the answer to something like this really is that you have to go towards scheduling policies where deliberately a processor will be kept idle. Okay, so you have to go towards non-work conserving schedulers. That is, just because a processor is free doesn't mean that you have to use it. Okay, because otherwise you end up with these anomalies. Okay, next issue. So in what ways do you think scheduling a CPU differs from, let's say, scheduling packet transmissions over a network, a radio? So let's say I have an Ethernet switch or whatever, a radio, and I'm sending kind of packets over it. And so you can imagine the same kind of real-time problems that we talk about, that tasks have deadlines, periods. I schedule the CPU. I could do the same thing for, let's say, a wireless link or an Ethernet link. In what ways is the scheduling setup different?
Serial is one resource.
Sure, CPU is one resource, right? Radio is one resource. I send packets over the radio. CPU is one resource. I run a task at a time.
Here I have multiple resources, multiple CPUs.
No, here I had multiple CPUs, but again, I'm back to now single CPU. Single CPU. So what I'm trying to say is the other place where there's a very precious resource is bandwidth, network interface. Okay, so I have a bunch of packets, and I have to schedule those packets for transmission over that network interface. And so in CPU, we found that priorities based stuff with preemptive scheduling worked great. Could we use the same setting for, let's say, Ethernet card? And if not, why not? So packets and computing tasks differ in a very crucial way. That's what I'm trying to get at.
Dependency here.
Huh? Forget dependencies. No dependency. Independent tasks, independent packets.
So typically packets are sent in different chunks, and they have a header and a footer. So they have to go, in the same order. You cannot start sending one more packet.
Right. So exactly. So packets are non-preemptible. Okay. Or put it differently, if I preempt a packet, I have to restart from the beginning. A task I can stop in the middle, save the state, restart it when I'm ready to allocate it. Whereas packets, I cannot do that. So what is mentioning is packets, or whether it's Ethernet or radios or whatnot. Typically, at the beginning of the packet, there are a bunch of bytes, a bunch of bits, which are called as a preamble. And then you have the rest of the packet, which has the header, like the addresses and all, and kind of the actual data body. And then sometimes you will probably also have some trailing things like error codes and stuff like that. Okay, what's the purpose of that initial preamble?
It's like a handshake kind of thing.
No, there's no handshake. I'm just sending a packet. And the thing is, let's say I have an IP packet. So IP packet has defined, or has very well defined fields in it, right? Why can I not just start sending the first byte of my IP packet to you? Why do we put that preamble in front of it?
It's to differentiate from noise, that you're actually sending a valid packet.
Kind of, but not quite.
Sequence number. The sequence number.
No, that's usually part of the header.
Doesn't that first bit say where the thing is going? So if you just
No, that's part of the header.
Sorry,
We're all talking about addresses, huh?
what's the question again?
My question is that when I'm trying to motivate why I cannot just preempt a packet in the middle. Okay, so whenever I send a packet, at the beginning we send this preamble. These are usually some fixed patterns of bits. And my question is, why do we send that? Every communication system that pretty much you use has that. Okay, at the beginning there is stuff which goes out, which plays some very critical role.
For synchronization.
Exactly, exactly. So it's for synchronization. So the problem that you have in communication systems is, I'm sending you a packet. Node A is sending a packet to node B. Node A has a clock, and it starts sending bits out according to that clock, okay, or symbols or whatever, right? Node B has a clock, it's sampling those bits. Both of us agreed that, okay, my clock is 100 megahertz, your clock is 100 megahertz, so I can send things out one symbol every 10 nanosecond. But maybe your clock is slightly different frequency than mine. So if you were to not do anything, if I were to send these things out, you will start sampling them, but you are sampling them a little bit differently than what I'm transmitting it at. And as a consequence, after a very short number of bits, we'll have a problem. You'll be actually sampling, because your clock, I said mine was 100, yours was 100.1, so your clock is a little bit faster than mine, so pretty soon you will hit a situation where you will sample the same bit twice, right? So we need to somehow synchronize our clocks so that we sample correctly. So the idea behind sending this initial preamble is it's a very known pattern of bits which are sent, and that helps train your clock to be at the same frequency as mine, or more precisely, you will learn that with respect to your clock, what is the frequency of my clock, what is the relative difference, and then you will, and then the receive side will apply a correction to its clock. It will sort of tweak you can imagine many different ways. It can count the edges correctly, or maybe it can actually change the clock frequency, but that's called frequency synchronization. So you synchronize the frequency, and then once you have synchronized the frequency using that preamble, then you can go ahead and sample the things, okay? Now the problem with this is that we synchronize this thing at the beginning, and then once I have synchronized the clock frequency, then we use it for rest of the packet. In fact, this is why you cannot send an arbitrarily long packet also, because if the packet is too long, then after your clocks are still drifting away, we'll learn more about it in subsequent lectures. So after a short while, synchronization will be lost, and we'll again start having a lot of bit errors. So when we say Ethernet has whatever 1536 byte packet length, that basically is because this initial synchronization is only good for so long. Okay, and of course we don't want to complicate our systems by having very costly stable clocks on either side also. You could imagine putting atomic clocks or whatnot and then be good for a long time to come, but that's not worth it. So the way packets are sent is at the beginning there is this training stuff which trains the receiver so that it can work with it. Now imagine if you were to do preemptive stuff, which is stop the packet in the middle after, let's say, halfway through the packet, and then let some other packet transmit, and then come back to this packet and say, let's start where we left off. Guess what? We cannot do it because you have lost that training. A lot of time has passed. So when it comes to communication systems, we have to let go of preemption. So either you have to, so there are two ways out really. One is we basically say, okay, we'll preempt, and then every time we preempt, we are going to restart all over again. Okay, we are going to send the packet from the beginning. So it's as if in CPU terms, whenever I preempt a task, whenever an interrupt comes, I have to restart the task which was preempted right from beginning. And of course, not a very wise thing to do. So the other alternative is that we look at theories which can deal with non-preemptive priority-based stuff. Okay, that is, if a new task became ready, a higher priority task comes, I will wait for the current task to finish before I give the CPU to this new one. Or in case of packets, I will wait for the, even if a new packet arrived while this packet is in progress, I will wait until this packet finishes before I will give it to the next one. No preemption allowed. So that is one very critical way in which real-time communication, or communication where you're trying to do deadlines and all, has to differ from sort of tasks on a CPU. I cannot preempt packets in the middle. Or another way of saying is, in a CPU, I can preempt at instruction boundaries. In case of communication, I can only preempt at packet boundaries. Okay, and while there are some communication systems where the basic unit is small, like so-called ATM networks, asynchronous transfer mode, there each packet is 53 bytes, or they call it cells. But in things like Ethernet and all, our packets are 1500 bytes. Or in case of newer Ethernets, there are so-called jumbo packets which are even larger. Okay, so and I have, it's all or nothing. Either I send all of it, or kind of wait. So non-preemptive scheduling is what gets used out there. So in many, so many settings, basically maintaining sort of preemption, arbitrary preemption is very hard. So non-preemptive is basically we are forced to use it, and they are therefore a lot easier to implement in these kind of settings. Now the problem with non-preemptive is that the theory is much harder. The results are a lot harder to grasp. So which is why the progress in it took actually much later. It turns out, I mean, one would imagine preemption would be harder because we are talking about arbitrarily interrupting things and all. But it turns out that from a theoretical perspective, in terms of saying whether a set of tasks or set of packets is schedulable or not, is a lot easier to answer for preemptive cases than for a non-preemptive case. Non-preemptive does have one advantage. We will never run into our priority inversion type of issues and all. If something locks a resource, it will release it before it finishes, and we are not going to preempt it. Okay, so non-preemption is a little bit like saying disabling the interrupt. So imagine if I were to be running my static priority type systems, but every task was to disable the interrupt at the beginning and re-enable it at the end, then we'll have non-preemptive scheduling. So results from this thing came later on, but otherwise the models are very similar. Okay, so I have a set of tasks which have a computation time and a period associated with them. You could also have, if it's a non-periodic task set, then period actually represents the smallest possible gap between tasks, and then just like we had the notion of concrete and non-concrete things. So the idea is if we know when the first task in a first job in a task was released, then we will then we say we know the phase, and therefore in that case it's a concrete task set. In other cases we don't. So for example, let's say I have this task set where 3 is the computation time, 5 is the period. This guy has 4 is the computation time, 10 is the period. If I if I look at this, say, then basically what I'm saying is you have to tell me whether this is schedulable or not, irrespective of whenever the first copy of this comes and whenever the first copy of this one comes. But alternatively, I could also have, I can give you when the first copy came. Okay, so I can say, okay, imagine a system where first copy of task 1 came at time 0 and first copy of task 2 also came at time 0. And it turns out that this guy is schedulable. Okay, non-preemptively schedulable. But if I gave you this task, that is 3.5 came at time 1, 4.10 came at time 0, then it is not schedulable, it turns out. Okay, and so there is a subtlety out here, which is an algorithm which says that it can schedule a non-concrete task set is saying that it is able to schedule it irrespective of whatever is the arrival time of the first task. Whereas an algorithm which is for concrete tasks is basically going to be able to say, okay, can I schedule this or not? Can I schedule this or not? Okay. So if I say I have a universal or an optimum algorithm for concrete tasks, then it's basically making the claim that if this task set is schedulable, it would be able to schedule it. And if it is not schedulable in principle, then it cannot. For a non-concrete task set, for something like this, where we are not given the phases, the same thing, except that now if an algorithm says that it is able to, it is optimum, then it should be able to schedule all versions of these tasks, irrespective of phases that are schedulable. Going back to our preemptive case, rate monotonic and EDF were looking at these kind of tasks. Okay, they were looking at where no initial phase was described. So I'm going to skip through all the theory out here and kind of just present kind of the main result out here. So the main result is the following. If I have periodic tasks, non-preemptive scheduling, and I give you just a set of tasks, that is, there is no initial phase prescribed, then non-preemptive EDF is the best algorithm, is the optimum algorithm. That is, if it cannot, then nothing else. So what is non-preemptive EDF? In normal EDF, we had the situation that whenever a task became ready and if its deadline was earlier than the deadline of the currently running task, we would preempt the currently running task immediately, run this new task. In this particular case, in non-preemptive EDF, currently running task has to finish, and at that time we would look at among our ready tasks and which one has the earliest deadline. Okay, so it's the equivalent of a Ethernet card, for example, which has a queue of packets. So the software keeps sending it packets, and what this guy is doing is, moment it's done finishing sending the current packet, it now looks at its buffer and says which one of the packet has the tightest deadline, needs to reach the destination the soonest. It will pick that one. It will not preempt anything going. So what the result out here shows is that non-preemptive PDF is optimum both for periodic task sets as well as sporadic. Sporadic meaning that I'm given the minimum inter-arrival time between packets or tasks, but if I have a set of concrete tasks, that is, I give you a task and I also give you the arrival time of the first task, and then after that they are periodic. Then for sporadic case, non-preemptive EDM is again optimum. That is, if it cannot schedule it, nothing can. But this problem, that is, I have a set of periodic tasks for which I have given you the initial arrival time of the first job. And now I want to find what is the universal algorithm. Well, we don't know whether an efficient algorithm for this exists or not. What about how hard it is that I give you a task set and saying how hard it is to decide whether this task set is schedulable or not. So again, I'm giving you a bunch of tasks. I'm telling you whether they're periodic or I'm giving you the minimum inter-arrival time. If I give you the set of tasks, no failures given, then we have non-preemptive EDF, and this schedulability test is very, very much like the one for EDF. So it is pseudo-polynomial in time, and I have to kind of check it over a duration of time. Same thing out here. But if I give you a periodic task set, and I also tell you when each copy of the task, first copy is arriving, then that is a NP-hard problem. Okay. So ironically, one would have thought that periodic case or the concrete task set would be the easiest, but it's not. It's actually the hardest one to do optimally. Okay, so that's non-preemptive, and sort of a lot of subsequent results, and there are many very efficient realizations of scheduling and other scheduling criterions that have emerged in networking literature. So things like fairness. So not just so the view out here is deadline, that we care about a deadline, but there are other ways networking people have often dealt with, which is instead of worrying about deadlines, worry about how much bandwidth we are giving. What is the rate at which bits are flowing for a particular task, particular flow. And so there are a lot of interesting results in that. Time permitting, I'll come to them, but there's kind of a rich literature out there. One constraint that exists in networking quite a bit for high-speed routers and all is that all of these algorithms have to be implemented in hardware because they're running at tens of gigabit per second or kind of speed. So speed becomes a constraint as well. A final class of scheduling algorithm that I wanted to sort of touch upon are those which are inspired by economics. So economics fundamentally is the science for efficient resource allocation at the societal scale. We basically leading theory being that various kind of market mechanisms let the system allocate resources very efficiently. We have notions of auctions and price and lottery and things like that, and kind of equilibrium emerges where sort of everyone is sort of the happiest and we are in a stable situation. So there has been a lot of work where people have taken ideas from economics and applied them to various kind of scheduling problems. One which kind of I'm highlighting, but by no means the only one out there, is something which decided to take lotteries as the inspiration. And the reason I picked it up is because it's actually available in Linux also as an implementation. So it's one of the more commonly available things. So these algorithms go a little bit more, they move away from the world of hard guarantees to softer guarantees, softer notions of things. So the basic idea out here is that I have a resource, CPU or a network or whatnot, and I have a bunch of tasks. And what I want to do is I want to divvy up that resource among these competing entities such that the relative execution rates, that is the relative share of the CPU that they are getting, is we are trying to guarantee that. So we are kind of trying to say that, okay, this task will get 1/3 of the CPU, this task will get 1/2 the CPU, this task will get the remainder of the CPU. So we are really talking in terms of the throughputs that are there. Now the problem, of course, that happens in this case is that I cannot simply say, okay, let's take the time of 10 time units, give 3 time units to task 1, 5 to task 2, and 2 to task 3, because those tasks may not be ready at the time that they need it, right? So it's not simply a matter of a central scheduler just kind of parceling out the time slots, because what if a task which requested 1/3 of the CPU was not actually ready when you're offering it the slot? Other complications may arise also for a variety of things. So the lottery mechanism is kind of the following, that in a lottery, your chances of winning depend upon how many lottery tickets you purchase. So if there's a pool of 100 lottery tickets and you purchase 30 of them, then every time the lottery is conducted, you have a 30% chance of winning. So what lottery scheduling does is takes that as an inspiration, and at every time tick, if you may, the operating system conducts a lottery among the tasks, and then probabilistically selects a winner, and that winner is based upon how many lottery tickets each one of the tasks had. So each round it's conducting this lottery, selecting a winner. That winner gets to run for the next time slot. So this is basically kind of trying to divide the resource, CPU time or network interface time or whatever, in proportion to the number of lottery tickets that one has. So the right to the resource in this case is defined by the number of lottery tickets. And so essentially now if I want to change the relative rates, I need to basically give them relatively different number of tickets. So you can now imagine a lot of other creative things to be built up. Let's say, for example, task 1 has relatively few resources. It has few lottery tickets, so it doesn't get a chance to run a whole time. But it has blocked some shared data structure which important task needs. So now in our normal framework, we would have said this is priority inversion. Let's give the priority to this lower priority task. What would you do out here? So again, the scheduler out here is very simple. Every time tick, every scheduling tick, it is basically going to run a lottery, and then based upon so essentially toss a coin and kind of decide based upon the number of lottery tickets held, which one wins. So my question is the following: imagine in this kind of a setting, a task has grabbed a resource, grabbed a shared data structure, let's say a semaphore, and is now blocking another task which has lots of lottery tickets, is blocking it from running. So if I were to ask you to kind of design something equivalent to a priority inversion mechanism, what kind of things can you do?
You give the tickets.
You give the tickets to others. So temporarily give the tickets to others, right? So tickets become the vehicle by which you control the relative importance. So in this case, the tickets would be transferred by the task which is being blocked to the task which was otherwise poor but is temporarily holding this thing. So you kind of do this transfer of the ticket. Okay, so I could use ticket that way. Now let's imagine I have applications and I have given this different applications different number of lottery tickets. But within my application, I have threads, and those threads have relative importance too. Right? So you can take this mechanism a level deeper, and you can basically say, look, whatever resource I have given to the application, I have to deviate among these threads within that application, and kind of the same argument applies there as well. That is, I can have within each application, I can assign lottery tickets to each one of the thread and then relate them to the overall tickets that this application is holding. So these kind of concepts are part of this approach. So scheduling is probabilistically fair in this particular case, number of lotteries that given by the standard binomial distribution, and typically, so these kind of things are really meant for general purpose operating systems where there is a time tick, and at the time tick scheduling takes place. So that's quantum is usually 10 to 20 milliseconds, somewhere in that range in typical Unix, Windows type operating system. So normally the scheduling lottery will take place at those boundaries unless a currently running task gives up the CPU. Maybe it blocks for something, in which case a lottery is conducted immediately. So this notion of lottery sort of became a little bit kind of a nice vehicle for to reason about the resource allocation and all. So lottery basically represents, in this case, a right to a resource, and you can transfer that right to a resource. You can play games with this thing. One issue which comes up also out here, there are other things you can also do. You can temporarily inflate the value of a ticket, so you can suddenly kind of want to give a task more importance. You can assign a higher value to their ticket temporarily. So like if you can have almost like a notion of currency attached to this. They call it inflation deflation. So tickets have currencies. Another issue which comes up out here is the following: that let's say at a scheduling test, lottery was won by task number I, but task number I is not able to run because it is waiting for some resource. What should you do in this particular case? So now you can imagine that. There's no kind of right answer to this thing, right? I mean, one way you can say, okay, you were not ready to run, so why don't you take a rain check and accumulate this right for a later usage? So next time that you run, you get a higher priority, and so on and so forth. There's a problem with this, which is a task may keep sleeping for a long while and then suddenly take all its accumulated rights and then in one go starve everyone out. So you need to have some control over this kind of a process. So what they do is they do if a task did not consume all the resource that was given to it, then we inflate the value of its ticket by a certain amount, but not entirely. So you kind of keep this process under control. Another situation under which something like this happens is the following. Imagine a radio where I gave a particular flow, a particular task, the right to send the packet, but the channel happened to be bad at the time. So it's the equivalent of I gave the CPU to the task, but right when it gave the CPU to the task, the CPU heated up and was unable to run the task, or maybe the frequency was lowered dramatically. No fault of the task, but we just happened to assign the resource to it when the resource was in a bad state. What should we do in that case? Again, no single correct answer. I mean, you can basically say that, okay, tough luck, no promises made about, we are just assigning you the resource. Whether the resource is in a good state or not is not my concern. Or alternatively, you may try to compensate for it sometime. Okay, so you can say, okay, we gave you a resource, but the CPU speed was slower during that time because of thermal reasons, so therefore we will inflate the value of your lottery for the next time. So all these kind of games can be played, and the nice thing is that lottery as an abstraction is particularly amenable to these kind of games because I can bump up and down the value and all. If you were to try to do these things in, let's say, rate monotonic setting or earliest deadline first setting and all, it's pretty tricky to pull these things off. You cannot do these kind of compensations and all. Of course, there's a penalty out here. The penalty out here is that we have a softer notion of what we are doing. There's no deadline that we are promising. We can say something stochastically, but we can certainly not say anything in a guaranteed fashion out here. Having said that, this is kind of a nice way of thinking about resource allocation, and there are papers with other kind of analogous ideas, auctions, reverse auctions. These kind of things are also present and implemented as scheduling algorithm. This particular one, as I said, is available in a variety of forms. So then there's an implementation in Linux. There is also hardware level implementation. Some of these buses and networks on chips make use of lottery scheduling because it's actually pretty easy to implement also. So it's something which sort of has been pretty popular in literature, I guess. So there are variations, inverse lotteries, applying it to multiple resources, and so on and so forth. So kind of quite a bit of stuff out there. Okay, so that was scheduling. So one thing which I have not covered in scheduling much together is the one when we do real-time considerations for non-CPU resources. We talked a little bit today about what happens when we have a communication link and why non-preemptive stuff is necessary out there. But having said that, that part of the literature is pretty deep and extensive, and so besides the EDF stuff that I mentioned, there's a lot more that exists in on how you implement real-time scheduling for communication links, which I didn't go into. But if you take like the networking class in computer science, 215 or 218, they cover these kind of topics. So next thing, so the reason we were doing all this scheduling and all was in part because time is a precious resource, and time fundamentally plays a very important role in embedded systems. That's how they interact with the physical world. So this and the next slide set, we are going to look at these issues of time and clocks and what the technology is and what are kind of the issues and all out there. So how is time used in systems in a very abstract way? So what do you think? Why do systems need to know time, or application need to know time? What are the different reasons?
Coordination.
Okay, so could you elaborate more? Coordination for sure, but what kind of? Give me an example.
If we are two nodes or two computing devices that are communicating together, I am expecting to do something at a certain time. You should be aware. Both of us should be aware of the time.
Okay, so one is coordination, as in something happens, both of us have to react, and we are going to react together. Okay, it could be missile coming, two guns have to shoot together so that they both hit them together and destroy the missile. Okay, so coordination. What else? And there are other things you can coordinate, right? It could be coordinating access to data. Okay, coordinating a whole bunch of things. So knowledge of time can assist out there. If all of us knew kind of the universe time, then we can do actions simultaneously. We can do actions in some desired sequence, and so forth. What else?
Resource management.
So explain that.
Okay, so if you are, both of us are sharing a media, common media, we can be assigning time slots for each of us to share it. Like
okay, so that's part of coordination. But yeah, okay, kind of related to that. Okay, what else? Anyone else? Any other thoughts? Anthony.
If we want something to happen at a certain time.
Okay, sure.
Like we want an alarm.
At a certain time, at a certain rate, at a right. I mean, all those things. Sure. What else?
The access of certain data, like when was the data collected?
When was data collected? So time stamping a piece of data. Okay. What else?
Some security applications. There is some techniques at which a public key or a key for validating the data is
okay. So authentication. I mean, I issue you the right to do something for a certain amount of time. How do you know that's true? So right. Okay. What else?
All our scheduling is dependent on time, deadline.
Yeah, but those are no. But why do we have deadlines and all, right? I mean, think about that. Okay, so what? I mean, there's something. There are other very fundamental reasons why system needs time. Systems need time. Okay, let's say I'm observing a target, and it could be either, and all I see it as a circle. Okay, a target. Okay, and I want to classify whether it is a bike or a fast-moving vehicle. How would you classify it? You need to know the speed. To know the speed, you are going to see distance traveled over time. So you need time to understand physical quantities, right? I mean, a lot of physical world tasks are going to depend upon you being able to say something about speed or some other time-related values. Okay, so measuring passage of time is important for system to interact with physical stuff. So whole bunch of things. Now, interestingly, time is also obviously a quantity in physics, a quantity in philosophy, and sort of people have dealt and thought about it many different ways. So there are many different interpretations of time. In fact, if you even kind of try to ask yourself, what is time? It's a pretty incredibly hard question to kind of ponder about. Okay, but having said all of that, from practical perspective, reasons. I mean, computer systems, embedded systems in particular, make use of time in a variety of different ways, in many different senses, for many different purposes. One of the realizations which has also occurred in recent years is that many times we develop elaborate protocols because we don't have good quality of, we don't have good knowledge of time. So what I mean by that is, let's imagine we are, there are all these elaborate protocols to prevent, to lock data structures, let's say, or lock a resource, like, or for example, figuring out whether computer 1 wrote to the file first or computer 2 wrote to the file first, right? I mean, so absence, if we don't have knowledge of physical time, then we kind of rely on all sort of protocols to make sure things happen in a right order and so on and so forth. One of the big changes which are taking place now is that as the knowledge of time is, knowledge of accurate time is becoming more commonplace in computers, there are things you can do much more easily than otherwise. So for example, the way, I mean, one of great recent examples is that the way Google reconciles and keeps data coherent across its databases, across different data centers, is standard techniques for a lot of message exchange, kind of logic, establish some logical consistency. Now what they do is they make use of absolute timestamps and uncertainties associated with them, and they have a much faster way of kind of reconciling changes into a database, okay, because everyone kind of knows time to a much higher degree of accuracy than before. So time is important in general purpose computers, but time is even more important in cyber physical, embedded, IoT type systems. Okay, so historically, lots of work on time. In fact, one of the very first driver applications for developing better clocks was just navigation, that is being able to sort of, for the ship-faring countries, for them to go far distances. So latitude can be found by measuring the position of the sun and all, okay, so that you can do, but to find longitude you need time. Okay, that's the only way you can kind of do it accurately. So back in 1700s, there was actually the equivalent of today's X prize, which in that case was 20,000 pounds, which is $2 million today, was offered to a person who could localize a ship within 30 nautical miles, and this needed a clock that could be accurate to within 3 seconds every day. Okay, so this was won not by some sophisticated physicist or academician and all. It was won by some watchmaker, some sort of less sophisticated person working in a village, and who kind of made the timepiece which kind of won this award. So and it changed, it had a huge impact in the sense because you could accurately localize in the middle of an ocean. So lots of fascinating work. Go ahead.
Did you say what the picture from the very first slide was?
Okay, anyone? What is it?
UCB board.
Huh?
It looks like a UCB board.
Anyone else? Yeah, it's an oscillator. It's a tuning fork type oscillator. It's inside of that. Yeah. Okay. So we'll come to that. come to oscillators, but yeah, it's looking inside that. Yeah. Okay. So lots of work. I mean, starting with the early sundials and pendulums and stuff like that, to nowadays. I mean, you have chip scale atomic clocks and all sort of other fancy stuff which kind of exists. Okay, so lots of variety of clocking technologies. By the way, incidentally, if you're ever in London, in South London area, there is this Museum of Science and Technology out there, where some of the most wondrous devices from kind of the Renaissance period science, if you may, 1700s onwards exist. They have a huge collection of things relating to time. I mean, there's just fascinating exhibits out there. So if you are ever there, visit it. And of course, all steam engine and all sort of pretty cool stuff. Okay. Anyway, so time basically, the unit of time, of course, is second, and the way it is defined is in terms of a certain number of transitions of the cesium atom. So this is kind of a philosophical point. There is no such thing as an absolute notion of time that is defined by the laws of physics or anything like that, right? I mean, we decide to call that many state transitions of the cesium atom at a particular temperature to be what we call at a second, and everything else is basically relative to that. Um, at this stage, currently, the accurate clocks can keep time to within a fraction of a nanosecond or even somewhat better, and that translates into a second of error over millions of years. So that's terrific. And every other physical constant and all really ultimately kind of depends upon this particular definition and definition of time. So like what is a meter and all this are kind of all defined in terms of that. Now there is a global absolute time coordinate that we have established, which is called the UTC, and it's basically a bunch of atomic clocks. They take a weighted average of that, and then once in a while they kind of correct it, and there are always controversies. Like recently America proposed that we should no longer add leap seconds, and that raised a lot of uproar and all. And this has also been a source of national pride and all. So where is the prime meridian, that is relative to which UTC is measured, and of course it's the GMT or whatever, Greenwich in UK, which is that. Now, time, what there are many different ways you can think about time. So that was kind of time in terms of a second as the unit, but you can also talk about time which is purely as a logical concept. That is, time doesn't have to be about a rate relative to cesium atom. It could also simply be a sequence number. So something happened later than earlier if it has a higher sequence number. We don't assign any rate of change to those numbers. And so in example out here, I have processors and there are events happening at those processors. Some of these events are because one processor sends a message to another processor. So like in this case, this is a send event, this is a receive event. And maybe for certain purposes, the only thing I care about is whether an event happened before or after another event. So in this case, looking at this, we can say E23 happened after E22. We can certainly say E23 happened after this particular event to the bottom left, but we cannot really say whether E22 happened before or after this one because there is no enough information for doing it. So in this case, I only care about ordering, and that's where we leave it. So, but we could take this thing and embed it in some sort of a time coordinate system, and then we could certainly argue about whether this event happened before E22 or after. Now, unfortunately, even that is a little bit tricky because it depends if this is, I mean, we can answer these questions in a non-relativistic world. We are close to the phenomenon and everything. But if you are in the relativistic world, then whether an event happened before or after depends upon the observer. Depending upon the observer, it could see it in different ways. So things get trickier in other areas. But leaving those aside, I can have logical times and I can have time embedded in a physical dimension of some form. We need accurate time for a whole bunch of purposes. GPS is possible because we have accurate time. Okay. So in general, localization, ability to find one's location in variety of different settings, even things like you go to Home Depot and you buy these laser rangefinders where you kind of click them, they bounce the laser beam at the opposite wall and then measure the thing. They are measuring time very precisely, otherwise they will not be possible. So if you sort of, or earlier example that we were doing, our ability to communicate. So receivers have to sample bits. That won't be possible unless they could measure time duration very precisely. So being able to know time, time either relative to an absolute coordinate system or passage of time relative to some reference oscillator, cesium, atom transitions, for example, these are just around us in many kind of different ways. So communication becomes possible. Sensing, same story. If I'm sensing or radars and all, they all have security, coordinated action. There's a pretty cool video out here of two robots manipulating a fragile object, and very precise coordination is needed because if you don't, it will crush it. Okay, so precise coordination navigation, which we already talked about. So a whole bunch of things out there. So how do we measure time? So if we think about sort of measuring time, there are really fundamentally two things that constitute what we call as a total clock. One is an oscillator, some sort of an oscillator which generates a waveform with a certain frequency. Now, implied out here is, again, there is nothing God-given about like frequency and oscillator. All of this is really relative to that one oscillation of this pendulum correspond to some n oscillations, n transitions of the cesium atom, and that's how we ascribe a certain frequency number to it. So everything for us is back to our definition of saying that some certain number of cesium atom transitions constitute what we call as 1 second, and therefore a certain frequency. Okay, so there's an oscillator which somehow magically we have calibrated against the cesium atom directly or indirectly. And then there is some sort of a counter. Every time this oscillator ticks, the counter advances by 1. Okay, and if you think about it, every clock could be viewed at this way. There is an oscillator and there is a counter, and then as an application or a system or a software, we read this counter. Okay, atomic clocks are cesium atom as the oscillator and a fast electronic counter of some form kind of doing it. So now, of course, faced with this thing, there are a lot of other issues which kind of come up and all. I mean, of course, this oscillator may not be perfectly stable relative to this. We cannot say that this is unstable because there is no such thing as saying that cesium atoms thing is unstable because that's how we are defining things. Okay, if it changes, I mean, there's no, it's relative to this. So this is our reference. Okay, but we can certainly talk about due to friction, a pendulum slowing down or whatever, aging or whatnot. Counters have issues too. Counters have to represent numbers and they may overflow and all. So counters wrap around and all those kind of issues come up. So in terms of our computing systems, if we kind of look around, look at it in a somewhat more abstract fashion, then we can say that our systems look like the following. There is some sort of what is called as a resonator or a passive resonator. So crystal, tuning fork, these kind of things, which are capable of oscillating when given energy and when continue to give energy. Okay, we have to keep giving energy to these resonators because why? Anyone? So I guess what I'm saying is there's no such thing as a resonator will just keep oscillating forever on its own. Come on. Why does a pendulum not keep oscillating forever? Friction, right? Everything has some sort of a loss, right? I mean, so you have to supply it energy to kind of keep going. But what your hope is that they have a very well-defined, narrow or precise frequency at which, when given energy, they will keep oscillating. Okay, so there are many different forms of resonators, and then associated with them would be some sort of a power source plus some additional filters and stuff like that, which will keep the oscillation going. This assemblage is what we call as an oscillator. An output of this associated with some other additional circuitry would be what in computing systems we call as the clock signal. So clock signal is some sort of a periodic digital waveform which helps regulate everything else in the system. This is what we feed into registers. This is what we put into our serial lines and stuff like that. Okay, so that drives everything. This clock signal its frequency can be changed by playing circuit games. You can certainly divide the frequency, but you can also multiply the frequency by using things such as phase lock loops, and also you can kind of bump up the frequency, you can lower the frequency. More typically, we will feed these things into some sort of a counter. So typical embedded processors like the one we have seen earlier in the course, they have bunch of counters, usually 32-bit, 64-bit, things like that. And this, there we maintain numbers, and then our software can read or write these counters. And implied in this thing is that there is some function which takes the values of this counter and maps it into our time coordinate system. So if our time coordinate system is, let's say, UTC, then somehow we will have a function which will say, when the reading is this, that means such and such UTC time value. And of course, there are additional issues out here. I mean, you don't have enough number of bits and all, so maybe you will maintain some additional bits in the software and all, but deep down, this is kind of what exists. Oscillators, this part, really care only about frequency. So their job is to give you a stable frequency, stable thing. At this point, the signal may be analog, or it may be like a sine wave, it may be digital, depends upon kind of precise nature. The point is, the focus is on providing stability. And what also additional things which are also important is that how much this waveform is jittery or not. So like for example, it could be that I may have an oscillator where if I look at a 1 hour window, if its nominal frequency is 1 hertz, then over a 1 hour window it will give me precisely 3600 oscillations. And that's great, it's very precise. But maybe in any given shorter windows it may have jitter, so maybe cycle to cycle there might be some jitter happening, but they kind of cancel out over the long time interval. So phase noise kind of refers to kind of the jitteriness that exists in these waveforms. So oscillators care about frequency. Clocks care about other aspects of time also, which is what is the period, how much the error in the period is, and so on and so forth. Frequency stability, we'll talk more about it, is measured in what are called as part per million or part per billion. It's basically saying that if I'm claiming that my frequency is x, and if there is a tiny error in it, delta x, then delta x over x is what we call as the stability. And instead of expressing it in percentages, we express it typically in ppb or ppm. So for example, 1 ppm clock stability would mean that for a 1 megahertz clock, there could be a 1 hertz error. Okay, 1 hertz out of 1 megahertz, so 1 in 10 to the power 6. And the reason we use ppm and ppb is that we are dealing with very small numbers. Okay, these clocks tend to be pretty good. Time is kept by the hardware counter, which is updated by the clock signal. The clock signal increments the counter every so often. So we would believe that our clock signal has some frequency f. So every 1 over f second, the hardware counter is going to increment. So the resolution of that counter is 1 over f seconds. Okay, so that's the resolution. And then the counter at any if counter has n bits, so it will overflow. So at any given point in time, if the counter reading corresponds to frequency times t modulo 2n, because it's going to keep wrapping, and I'm going to have a floor function. So looking at this, you can see a couple of imperfections that exist in C of t, which is number one, it is quantized. Okay, so in between clock ticks, it doesn't advance, and number two is it overflows. So I only know the time modulo to the power n. So I have to keep track of that somehow. So quantization error, because if my clock is 1 megahertz, I can really only measure time to a 1 megahertz resolution, and overflow because I only have n bits which are out there. So smallest increment at which software can read the counter is called precision, and how close the timer is to UTC is accuracy. So usually we take the C of t and then we apply some mapping to it to come up with, let's say, a time in terms of UTC. So this mapping may include things like when did at the startup time, what was the counter value, okay, for example, and it could be other mechanisms. And once in a while, maybe I can add or subtract some numbers from this thing to correct for any error. But essentially, eventually, how close my time is to UTC is going to be my accuracy. So if my computer is saying right now 11:45:18, well, I don't know what how close or far it is from the official time, but NTP and all kind of promise that we should be pretty like within tens of milliseconds of what that time is. So oscillators, clocks, and time, these are kind of distinct concepts. So this is oscillator, this is the clock signal. Okay, I guess the whole thing you can call it the clock, and then this is the time is what we kind of read out of this hardware counter. So then, yeah, go ahead.
So the Y2K problem, was that the software or the hardware counter? counter problem or from code.
So Y2K problem was really, in a way, this N problem. Let me see. So Y2K problem, yeah, it was the N problem. Okay, so so what was happening was the following: that so not quite clear. Okay, so what's happening is that we take the reading of this and then we update some software data structure, which is where we, let's say we are maintaining our understanding of the UTC time, right? So we keep reading this hardware counter once in a while and map it into some sort of a software structure, which is where we are saying, according to my preferred coordinate system, time coordinate system, that's the time. And Y2K problem was that that data structure was maintaining only 2 year digits because it was assuming everything was 20th century. Okay, so it was a representation of that object in the software. These counters tend to be pretty short. I mean, let's think of it this way. Until not too far back, our computers were 32-bit. So 32-bit is 4 gig. We are running, let's say if you're running these counters at a 1 gigahertz clock, then every 4 seconds they're going to overflow. Okay, so you certainly cannot represent time at the human scales and all in this counter. Okay, this is going to overflow very rapidly. Okay, so within the operating system and all, yes, it will have access to this hardware counter, but then there is going to be a computed notion of time, which is what the OS maintains and which is what is corrected and updated and all whenever like something leap seconds to be added and whatnot and all. Whereas this guy normally is purely going to just run by updating the clock signal, nothing else. Okay, so Y2K problem is really representation within the software. Now, having said that, there are certain qualifications also. Our computers also have something called real-time clocks, RTCs. Anyone ever heard of them? What do they do? Any ideas? Like if you look in your motherboards of at least the older PCs and all, they have this little RTC and they have even a separate battery for it. What is their purpose?
I thought the battery was to maintain the like the settings in the BIOS. So that if you take out the battery,
Yeah, like if you
Yeah,
remove it, you can reset the password.
Huh?
If you remove that battery, you can reset the BIOS password.
Yeah, you can do a lot of other stuff, but it also maintains time.
It's still computing the time even when the power's off.
Yeah, so there's actually a chip on at least Wintel PC, there's a chip which has its own clock oscillator, is running on this watch battery, and it maintains time, which is how kind of the processor knows. Like if you say power up at 2 p.m., how does it know it's 2 p.m.? Okay, so it comes from that information. But once the system boots up, it no longer relies on that. Then it kind of goes and works off things. So it's called real-time clock. These are special chips you can buy, and in which case, year, date, all those things are actually maintained inside the chip. Okay, but they are nothing but kind of almost like a separate little microprocessor which is maintaining in software those things. And some of the Y2K bugs could even have happened there as well, Y2K like bug. I guess the next bug which is waiting to happen is when we run out of the standard 32-bit Unix reference timestamp, which is relative to January 1st, 1970 or whatever, something like that, which is when again things are supposed to break. Okay, we'll find out. Anyway, let's stop out here. We'll pick up this thing. So Wednesday we have presentations. So again, please remember to send me your slides in advance or bring them in PDF on a USB